My function z, or f of xy, depending on how you want to call that, here's how we get to it. We take the integral, we integrate this part with respect to x. So I integrate this section with respect to x. Now it gets a little funny here because we're taught in calculus, don't integrate with two variables. And what we're really doing is a partial integration. And I see a little notation here. I've never seen a partial integral notation before. And I'm interrupting myself just to make sure that I didn't see something kind of funny in this book. No, I guess I did. I don't know of an integration symbol for partial integration. But in the context of the problem, I'm going to take y as a constant. Y is my constant. I'll only integrate to the x terms. So when I do that, I integrate 3x squared, I get x cubed times my constant y, so I get x cubed y, plus, integrate this, integrate 8x, I get 4x squared times my constant y squared, so it's 4x squared y squared. And then we always have an additive constant because it's an indefinite integration. I have no limits of integration here. My additive constant, being a constant, could involve y. So we're going to call that g of y. Because in the context of this partial integration, a function consisting only of a function of y variables is treated as a constant. So z is equal to this function. Now, look what happened here. I took p, this part, integrated with respect to x, and I got my overall solution function. X cubed y plus 4x squared y squared plus g of y. But now, to figure out what this is, I need to take its derivative and set equal to q. Because remember, the partial derivative of z, or f, with respect to y is equal to this function. So now I take the partial respect to y of x cubed y plus 4x squared y squared plus g of y, and we get x cubed plus 8x squared y plus g prime of y. So let me explain that. We're treating x as a constant now. Y is now being treated as my variable. So this derivative, that's 1 times x cubed. Let me make that look like an x cubed. Okay. This derivative is 2y. 2y times 8x squared is 8x squared y. And then the partial of g of y with respect to y is the ordinary derivative, g prime of y. It's the ordinary derivative because there's no x in it in this term here. It's just y and any other constants. All right, now I set this equal to q. Okay, x cubed plus 8x squared y plus 12y squared. So what happens here? Well, because this is equal to this function, I see the x cubes are equal, the 8x squared y, that checks out. G prime of y is 12y squared. So what's g of y? G of y would be the integral of 12y squared dy, which would be 4y cubed. 4y cubed. And technically that also has a constant, a plus c. I'm going to ignore that plus c though. I'll tell you why in a minute. But integrating this, I get 4y cubed. All right. So, wish I had a bigger board, as usual. But my answer is going to be z equal to x cubed y plus 4x squared y squared plus 4y cubed equals to a constant. All right, so let me write that out. I've got it here. I raised part of the board and wrote the answer. The answer of our function is going to be this x cubed y plus 4x squared y squared plus g of y, 4y cubed. equals to constant. Now why is that true? Because the original problem, we verified that it is an exact differential equation. Because it's an exact differential equation, we verified that it's equal to a differential of z, or a differential of a function f of xy. dz equals to 0. If dz equals to 0, when I integrate everything, I get z equal to a constant. So in your book, they would normally, most people leave this off and just write that's the answer to the problem. So here's the answer to this differential equation. And we can verify this, and perhaps we ought to. Anyway, in fact, let's go ahead and verify that. I think it would be kind of a good exercise, because I feel like it's a little bit of magic here, what we've done. And let's just see if this works. So, how would I do that? How do I get dx and dy into all this? Okay, well, I'm kind of thinking on my feet here, and let me see. If I take the derivative with respect to x of everything, derivative with respect to x of this entire equation. All right, it's we end up with implicit differentiation. I have a product rule here, so I have 3x squared y plus x cubed y prime. In fact, this is dy dx. So that comes right from the chain rule. And you may have known it in earlier calculus classes, implicit differentiation. Plus, this derivative will be 8x y squared plus 4x squared times 2y dy dx. So again, we have product rules here, which I applied. Finally, this part will be, this derivative will be 12y squared dy dx, and the right side is going to be 0. Alright, so I took the derivative with respect to x of that entire equation. Now I'm going to multiply everything by the differential dx. And when I do so, I have 3x squared y dx plus, here the dx is canceled, x cubed dy plus 8x squared y, 8xy squared dx plus 8x squared y, 8x squared y dy plus 12y squared dy equals to 0. Now if we separate these in the dx's and dy's, let's see, what do we get? I've got 3x squared y, the dx term. Okay, that works. Another dx term is 8xy squared. Okay, so these two terms fit right there. And then I've got my dy terms are x cubed. That's good. 8x squared y. There it is. And 12y squared. Those are the dy terms. Equals to 0. So, we're able to take this solution, take its ordinary derivative with respect to x, and come up with this differential equation. So in effect, I verified the answer, which means I guess I don't have to look at the book, but I will. Book solution for number 4 is x cubed y plus 4x squared y squared plus 4y cubed equals to a constant. There you go. So that's the long and short of it for exact differential equations. I'll work a few more examples here in the next videos.